Okay. The second part of 9.1 is a lesson on the intersection of two lines in three-dimensional space. So a visual aid for this would be two pencils, a pencil or pen, or something like that, or two rulers. If you hold the two pencils in the same direction but apart, that's the first case. This also occurs in two space. If you hold the two pencils together, they are parallel and coincident. So the first case was parallel and distinct. The second case, parallel and coincidence. This also happens in two space. Now, if you hold them so that they cross each other, they touch each other, but they're not parallel, there's a POI. And this also happens in two space or in the XY plane from grade 9 and 10. Now, this third case only happens in three space. So if you hold your pencils up so they're not parallel and they don't cross, those are called skew lines. Any angle, as long as they're not parallel and they're not touching, are called skew. There's no point of intersection, no POI. So this has infinite solutions, no solution, or no POI, and this has no solution as well. This one has a POI or a point of solution or a single solution, a single answer when you're solving equations anyways. Okay, those are the four geometries. Think about them, visualize them. To find the intersection of two lines, it's all about the parametrics again. And in this case, you take the parametrics of both lines and you equate the x components, the y components, the z components. You have three equations and you have two variables that aren't known. So there's actually an extra equation. The values of s and t you find have to work for all three parts, all three components, all three equations. All right. If there is a unique solution to the equation, there's a POI, okay, and the lines cross at a point. All right. So here's an example of that. And let's do the x components, the y components, and the z components. 0 plus, well, I don't have to write that, I guess. T is equal to negative 3. Oh, because it's 0s. Okay, so we have t right away. For y, we have 1 minus t is equal to 4 plus s. Okay. And we have 2 plus 2t is equal to negative 4 plus 2s. Now, because it simplified out so nicely, this is going to be relatively easy. 1, 2, and 3. I'm going to sub from equation 1 into 2. I get 1 minus, just watch your signs, 4 plus s, and I have s is equal to 0. I want to check with the other equation though. So again, I'm going to go sub 1 into 3. I'm going to check. I get 2 plus 2 times negative 3 is equal to negative 4 plus 2s. So then I get 2 minus 6 is negative 4 is equal to negative 4 plus 2s. 0 is equal to 2s and s is equal to 0. So I checked in both. Okay. So to find the POI, sub t is equal to negative 3 into line 1. So 0, 1, and 2 plus t is negative 3. So negative 3, 1, negative 1, and 2. So I get negative 3, 4, and negative 4. So the POI, the intersection of line 1 to line 2, is negative 3, 4, and negative 4. As soon as I know there's a POI, I can describe a geometry. These lines are parallel and not parallel. So line 1 is not parallel to line 2. and they are intersecting. So as soon as there's a single point of intersection, you know that. Just as an aside, and to double check, and you don't have to unless it asks you in some way to do that, you could put s is equal to 0 into line 2, and guess what you get? You get -3, 4, and -4, right? That reference point in line 2 is actually the point of intersection in this example. Okay, the next case, infinite number of solutions. So that means parallel and coincident. And you're going to get some true statement like they're showing there, 2 equals 2 or 0 equals 0. That means it doesn't matter what the value in S and T are. There is an infinite number of points, so S and T can be anything at all, and it will still intersect. Okay. Find the point of intersection of the following two lines. Show there's an infinite number of points. Okay. The first thing, there's different ways of looking at this. We're doing it the brute force method. So go ahead and set up your components or your parametrics. And I always put line 1 on the left. I have 0, and line 2 on the right, I have 0. Wow, that's really useful. For y, I have -1t is equal to -6 plus 3s. And for z, I have 2t is equal to 12 minus 6s. Now, I'm not going to work with with the x components or equation 1 because it's just 0 equals 0. I need to solve using these two. So let's eliminate t. So I'm going to take two equation 1s. I'm going to add equation 2 to it. Notice the signs are different, right? So -2t plus 2t, I get 0. -12 plus 12, I get 0. 2 times 3 is 6, so 6 plus -6 is 0s. I get 0 equals 0. Okay, so therefore, there are infinite solutions. And the only geometry that allows that is line 1 and line 2 are coincident, which also means they are parallel. You can't be coincident in a line and not be parallel. If you notice, -3 times direction vector 1 is equal to direction vector 2. If you look at the components of the two direction vectors, that is true. So we know they're parallel based on that. Direction vector 1 and direction vector 2 are parallel. And there we go. All right. Good for example 2. Example 3, the next case we have to deal with. If you get an impossible or a falsehood, like 0 equals 1 or 0 equals a number, there is no solution. Now, we don't know why there's no solution. We could have skew lines or distinct lines. Now, the people that wrote up these notes, you can see their names down there on the slide, really like doing this cross product thing. I'm not a big fan. I would rather see if there's no solution, I would just check if they're parallel or not. If they're parallel and there's no solution, then I know they're parallel and distinct. If they're not parallel and there's no solution, then I know they're skew lines, okay? So it still starts off with trying to find and that sort of thing. So go ahead and set up your parametrics and try to solve it, and then look at whether or not they're parallel. Pause the video and give it a go. Okay, so now the x component, the y components, and the z components. So I have -2 plus t is equal to -2s. I have 3 minus 2t is equal to 2 plus 4s. I have 1 plus t is equal to 1 minus 2s. I'm really noticing something about the x and y equations, and I don't have to. I could work with any of the two. I think any two out of the three, but let me number these up. If I take 1 and subtract 3, you'll see what I mean. I get -2 minus 1, which is -3. T minus t, the t's disappear. I get nothing minus 1, so -1. -2s minus -2s, there's no s's. This is, inconsistent. So no solution. So the lines are either, so the geometry could either be skew or parallel and distinct. Okay, those are the two possible geometries I'm faced with here. So the note said do cross product. I'm not a big fan. I would rather check if there is a parallel in the direction vectors. Is this true, right? I'm checking if the vectors are parallel, the lines are parallel. And I can see that -2 times 1, -2, 1 is equal to -2, +4, and -2. So line 1 is parallel to line 2. Therefore, the geometry is parallel and distinct lines. No solution, no intersection. Okay, there's the third geometry. And now example 4, we have skew lines. And again, I would not use cross product to check if parallel. I like looking for proportions. That to me is a lot easier. But go ahead and give example 4 a go, and then we'll go on to the next part of this lesson. Pause the video and try it. Okay, set up your parametrics. Hopefully you have that done now that you're rolling the video. So for the x, I have 1 is equal to -2 plus s. Oh, that's going to work out. For y, I have -1 is equal to 1. Oh, wow. Okay. And for z, I have t is equal to 0. Well, that seems fine. I mean, but look at what else we have here. We have x is equal to, oh, sorry, I have something wrong in my notes, and that's why I paused. This is false. Okay, this is impossible right here. So, this gives me s is equal to -1. This gives me t, but it's all impossible. So there's no solution. Okay, so it's either skew or parallel and distinct. I have to check. So is line 1 parallel to line 2? That's the question we're asking now. So 0, 0, 1 equal to k 1, 0, 0. K has to be equal to 0 for the x component to work, and it doesn't work. No k is possible, right? There's no solution to this. So the lines are skew. Line 1 and line 2 are skew. And there's the geometry. All right. Now we have this. And it starts off with something I said I don't like. So instead of this, if you can't find a proportionality between the direction vectors, then it's not parallel. If you can find a proportionality between the two vectors, then they're parallel. That's how I would check. And like I said, they're really big fans of this. This cross product idea. What you can do, R0 to R1 is actually a vector between the two lines. If that's parallel to one of the direction vectors, then they're coincident. If not, they're not. So rather than that, I would rather say, the this vector difference is proportional to the direction vector of one of the lines. If that's true, then they're parallel and coincident. If they're not proportional, of course, you could use direction vector 2. To be honest, once I get past the initial check for parallel, I'm usually just plugging in and solving. I think it's almost as efficient, but you can go to the next level. You look there, the difference vector between the two lines dotted with the cross product, the two, I'm not a big fan of doing a lot of that work that, just gives me geometry when I can just try to solve them. So let's go to the examples here. Use the vector method, use common sense to see. So I would always check for parallel first. And you notice that line 1 is parallel to line 2. I can say that, but I have to prove it. -2, direction vector 1 is equal to direction vector 2. Okay, so that's what shows me that. So great, they're parallel. And now I would go ahead and instead of trying to do something else, I would go ahead and just try to solve it. So I have the x, I have t equal to -2 minus 2s. For the y, I have 1 plus 2t is equal to -1 minus 4s. And for the z, I have 2 plus 3t is equal to -6s. So should be a t here. So what I would do is I would solve, I would sub this into the other equations, right? So that's one way to do it. I mean, I could do elimination as well, but so I'm going to sub 1 into 2, and I get 1 plus 2, -2 minus 2s is equal to -1 minus 4s. 1 minus 4 minus 4s equals -1 minus 4s. And I get the s is canceling out, and I get -3 is equal to -1. Okay, this is an inconsistent result. So no solution. Line 1 and line 2 are parallel, but there is no intersection, so parallel and distinct. Okay, try the next one. Are they parallel or not? If they are parallel, are they parallel and distinct? Or parallel and coincident? So line 1 is parallel to line 2. Is that true? Well, 3, 1, -1, 0 is equal to 3, -3, 0. So 3 U1s is equal to U2s. Okay, so yes, they're parallel. I'm noticing that the point 0, 0, 0, the origin, right, the 0 vector fits that first line. So instead of just plugging in the full parametrics, I can just plug in that point, or that 0 vector, and see if the second line fits it. I could have done that with the last one as well. Okay, so this one works. What do I get from this? Well, s is equal to 4/3. And from this one, I get s is equal to 4/3. Oh, okay, so there's a common point on the two lines. So they're parallel on a common point. So that common point isn't a unique point of intersection. So line 1 and line 2 are parallel, and coincident. Okay, they coincide. They're exactly the same line. All right. Try this one. Line 1 and line 2 are not parallel. How do we know? So we explain that the direction vectors aren't consistent. I'm going to sub 0, 1, -1, which is from the second line into line 1 using the parametrics. Okay, so here we go. So I have 0, 1, and -1 are the three components from line 2, that point. I have 2 plus 0t. Oh, right away. I mean, I can finish. But notice right away, this is impossible, isn't it? Let me just finish. It's 1 plus t, 3 plus 2t. So, this is 0 equals 2. It's an inconsistent result. So what does the geometry have to be? If they're not parallel and there's no solution, oh, my notes say that they're supposed to be. Did I do something wrong here? No, I don't think so. Oh, no, this doesn't work. This only works if it's parallel. That's a fail for me. I wonder if Huzafa was noticing. All right, I have to do the full parametrics. Why doesn't that work? Well, just because they're not parallel, if they intersect, the one point doesn't have to be common. So that doesn't work. Oh my goodness, I'm having a bad day. I'm blushing and embarrassed. So I have to use the full parametrics. 2 is equal to S. 1 plus t is equal to 1. And then I have 3 plus 2t is equal to -1 plus 2s. There I have an s. T has to be equal to 0. So I'm going to substitute that into the equation. I have 3 plus 2 times 0 is equal to -1 plus 2 times 2. I get 3 is equal to 3. So these points, they're not parallel. And intersect. Now, it didn't ask us to find what the point of intersection is. You could just plug in t is equal to 0. So the point of intersection is 2, 1, and 3, or s is equal to 2, which give you the same result. Okay. Sorry about that mistake. It's interesting. I'll just go over it because I was in autopilot and I obviously made a mistake. If there's parallel and there's one common point, then then they're coincident lines. If they're not parallel and you plug in a point, well, that doesn't mean anything. There's an infinite number of points that aren't common in two lines that intersect at a single point. All the other points on the line are not common. So you can't just try one point. So check the last one here. Line 1 is not parallel to line 2 since the direction vector 1 can't be in proportion of direction vector 2. So we have two geometries, either skew or intersecting. So we'll set up our parametrics and equate them. So we have 1 is equal to S. We have 0 is equal to, okay, right away we have something that can't work. We have T is equal to 0. This is a falsehood, right? So line 1 and line 2 are skew. No solution. And that's it for the lesson. Oh, looks like I got one more slide. Oh yeah, example 6 is a bust. I've tried to like example 6 and find meaning in it, and I don't like it. I've tried a number of times to enjoy it and find some deeper meaning. It's just a painful exercise, so we'll skip it.